Okay, this is our last piece for the second fundamental theorem of calculus. This one should be relatively quick because it's just taking some ideas that we've already worked with and moving them forward with what we know now, connecting some dots. I just want to there we go. This one. Okay, so I'm just going to do a couple of questions. That's really all I'm going to do here. So this graph is shown above. Let g be the function defined by g of x equals the integral from 1 to x of f of t dt. I have a big clue that I should be using fundamental theorem of calculus. If you watch my other videos, you already know what I want to say. You can pause the video now to figure out what exactly, what exactly is my clue that we are using the second fundamental theorem. And if you said my clue is that we have a function defined by an integral where a bound of our integral is x, congratulations, you got it right again. I'm pretty sure those are the same words I used before as well. So this is my clue that we're using the second fundamental theorem of calculus. Hopefully it syncs properly. There we go. Okay. And it's asking, where does g have a relative maximum? Well, what is our conditions for a relative maximum? It means that g prime equals 0 or undefined, and g prime switches positive to negative. Okay, and how do we find g prime? Well, let's just take the derivative of g. So d over dx of g of x, right this way, equals the integral from 1 to x of f of t dt. And reminder, what does our second fundamental theorem of calculus do? Well, the derivative of g to the x is g prime of x, and the derivative of an integral that has a bound of x is just going to mean we replace our variable in the integral with x, so it becomes equals f of x. So now g prime of x equals f of x, so now we just want f to equal 0 or undefined, and f to switch from positive to negative. So we're just threading the needle, or connecting our dots. Now that g prime is f, so we have a graph of f, there's no places where f is undefined, but f equals 0 at 1, 3, and 6. That's one condition, and where is it switching from positive to negative? Well, it's switching from positive to negative at 1 because we are above the x-axis, above the x-axis going to below the x-axis. So positive to negative at 1. From 3, it's switching from negative to positive, so that's not a maximum, that's a minimum. And at 6, it's neither because it's positive, positive on either side. So where does it have a relative maximum? It has a maximum at x equals 1. And boom, this is also a multiple choice question, but I'm taking away the multiple choice. There's one of them. Second question, okay. Let f be the function defined by that. On which of the following intervals is f increasing? I'm gonna save you the pausing. We're gonna be using second fundamental theorem, but I'm gonna let you actually try this one on your own. I want you to pause the video. I want you to try and figure out how can we figure out where f is increasing here. And come back and I'll walk us through it after you've tried on your own. Okay, so you should have tried on your own. Well, how do we know when f is increasing? Well, f increasing means we have a positive slope, which means that f prime is positive. So we're looking for where f prime is positive, so we have f of x. Well, let's take the derivative of f of x equals this integral from 6 to x of negative t squared minus t plus 6 dt. Eventually we'll actually learn how to do these integrals when we don't have a bound like this, but the derivative of f of x is f prime of x. And using our second fundamental theorem, we can just replace all these t's with an x. So we get negative x squared minus x plus 6. And there's our derivative. Well, where's our derivative 0? So 0 equals negative x squared, or where are our critical points is a better way to say that. Where are our critical points of this? And if we factor, I'll let you try and factor on your own. If you haven't already, you can pause it. I don't think I'm gonna spend time explaining how to factor. And when you end up factoring it, you should get something that looks like this. If you want to, you can even factor out a negative. So we can even say this is x minus 2, x plus 3. That should be the same thing, if I'm correct. Actually, I don't think I am correct, which I'm not really sure why it's not correct. It should work, but I'll just erase it, and I'll just work with what I have. So you factor it out. It's a little weird because we have a negative x, but this would show that 2 minus x equals 0, x plus 3 equals 0. So setting our factors to 0, we get that x equals 2. Oh, it does work. It does work. You can factor out the negative. Sorry, my mind got confused for a second, and x equals negative 3. So this is going to be our number line for our first derivative test. For this one, I'm going to choose 0. That's the easy one. 0, if I plug that in here, it's going to give us 6. So that's going to be positive there. If I go to the right of 2, let's pick 3. I'm actually going to use the factored form here. 3 plus 3 is 6. This is a positive number. 2 minus 3 is negative 1. This is a negative number. Negative times a positive is negative. And if I go to negative 4, negative 4 plus 3 is negative. 2 minus negative 4 is positive. This is going to be a positive times a negative. That's going to be a negative number. And I really would... if you can get to a point where you can just look at the factored form and figure out if the factors are positive or negative, that would make this process a lot quicker. But of course, if you want to substitute in, and that helps you do it. Okay, so where is f increasing? Where is f prime positive? It's positive from negative 3 to 2. So f is increasing from negative 3 to 2. Let me just make sure I'm... Yeah. And just a small bit of nuance that I'm going to add. This open bracket versus close, open versus closed, I've been told on the AP test, like, it doesn't matter that much. So you could also write it like this, and that's fine. Yeah, just a small little bit there. I don't really want to say anything more about that. Whatever brackets you choose, it doesn't matter. Okay, and that is all that I'm adding for our second fundamental theorem, and we are ready to move on to really get into integration after this. So thank you for watching.